My name is Trevett, and I'm going to be speaking for the next few minutes about bringing GPU acceleration into the web. And I'm going to be wearing two hats, bringing two perspectives to the presentation. By day, my role is VP of Mobile Content at NVIDIA. That means I work on the ecosystem for bringing cool apps to the web and mobile devices. But by night, I am the president of the Khronos Group, and we are defining many of the open standards to enable the software community to reach into silicon acceleration. And I'll be trying to make it clear which perspective I'm talking about at any particular point in time. So, companies like NVIDIA are bringing GPUs to pretty well every compute platform out there, from the smallest mobile device up to supercomputers, servers, and even cars now have quite a lot of GPU performance available to be tapped by browsers and applications. But traditionally, looking backwards into the past, browsers haven't made that much use of GPUs, but that's changing, and it's, I think, a good thing for the web ecosystem. And as we look forward, what are the most interesting platforms to bring GPU capability into the browser on? It's really mobile that's the new epicenter of innovation. If you look at the curves, the PC is kind of going flat. All of the new devices, the new user paradigms, the new types of applications that exploit the mobility and the sensors, as well as the GPU packed into mobile devices, are coming on Android and iOS devices. So any technology that we bring into the web has got to be accessible on those platforms as well as the more traditional ones. And the fact that the mobile is such a fast-moving platform is directly relevant to how we regard acceleration for the web, because suddenly, if you have a browser on a touch-enabled platform, the web browser becomes essentially a real-time application. It's got to be smoothly updated, ideally at 60 hertz. Whatever content is in the browser or the web app, there's no room anymore for slow, stuttery web updates whilst providing compelling and satisfying end-user experience to mobile users who are used to native application performance. Meanwhile, the number of pixels on mobile devices are far outstripping the larger displays that you've typically had on your PCs. People are striving for retinal resolution and higher. So we've gone from just a few 100,000 pixels to over 3 million pixels. Things have got dense, more pixels by a factor of 20 since the first iPhone has launched. And there's actually no end in sight. We're actually going to have even denser pixel displays. And with that many pixels to process and display at 60 hertz or more, we absolutely need to use a GPU, not just for the performance that a GPU can provide, but trying to throw that many pixels around in software through a CPU is the worst thing you can do for your battery consumption. A GPU is typically 10 or more times faster and more power efficient for doing imaging and graphics type operations. So if you value your users' battery life, you will use a GPU. So these two things together really make the use of a GPU in mobile browsers an imperative. And it's kind of worthwhile because the GPU roadmap for many vendors, this is the NVIDIA one, but the roadmaps from the other vendors are almost as good. We're seeing a factor of 100 times increase in performance in mobile GPUs over just a few years. So we are here today, Tegra 4, shipping from NVIDIA in devices. The next generation is particularly interesting on the NVIDIA roadmap because, well, I call it the singularity. We have desktop class GPUs coming to mobile. So in terms of functionality, there's now no difference between a desktop GPU you might be used to and the architecture of the GPUs you're enjoying on mobile devices, desktop class GPUs, desktop class functionality available through APIs. So this is a video out of the lab. This is a demo of that Logan device. This is a mobile GPU. Again, trying to show what mobile devices are going to be capable of next year in the market. This is a desktop demo, a realistic rendering of a face that we first showed on the Titan board, the GTC. That's a 250-watt board that plugs into a PC. Now it's essentially running at below half a watt on a mobile GPU. So there's a lot of performance, a lot of capability coming in these mobile GPUs. We need to bring it to the web. So how are these GPU capabilities being made accessible to the web and to web developers? Well, there's actually quite a diversity of different approaches and techniques and perspectives that are coming to bear here. First of all, the browser vendors themselves are increasingly using the GPU for their internal composition and rendering stacks. So that's capability that isn't directly exposed to developers, but hopefully you're noticing over time that the browser is becoming much more responsive because we're offloading the CPU more and more and loading work onto the GPU. On a mobile platform, that means the browser vendors are typically using a native API like OpenGL ES. But what about the developer-facing APIs? We have SVG, which is a well-established vector API. It would be great if we could get GPU acceleration for SVG and SVG apps. NVIDIA is working on some extensions to OpenGL to enable that very thing, and I'll explain more about that in a second. Probably the best-known GPU API right now in JavaScript land is WebGL. There's been a bunch of presentations about WebGL here in the program this week. I'll explain a little bit more about that and how it's developing and what the roadmap for WebGL is. But we also have another API, kind of the peer API to WebGL called WebCL. WebGL for graphics, WebCL for compute. That's a JavaScript binding of a compute API that we're bringing up into the browser, and I'll explain more about that as well. Finally, a couple things looking slightly into the future. There's no point having all the graphics performance in the world on a web application if it takes us a long time to download the 3D assets across the network. So we're beginning to think about compression and streaming for 3D assets. That's an initiative called glTF. And then last but not least, really looking out into the future for applications like augmented reality, a lot of sensor, vision, and camera processing. There's a bunch of native apps out there beginning to be developed to enable that kind of application, and we want to bring those up into the web for web developers as well. So I'm going to touch on each of these very briefly and try and give you an insight as to what's happening in each of these different domains. And so, where are all these standards coming from? Well, it's the Khronos Group. Some of you may be familiar with Khronos. We're an open industry consortium dedicated to creating royalty-free standards at the silicon software interface. So enabling developers to access silicon capabilities for graphics, for compute, for camera, vision processing, audio processing, media processing, etc. We're open to any company that wants to join. The quorum of the Khronos membership is the silicon community. So this is where really the silicon community comes to really figure out what the silicon roadmap it's going to be over the next few years. But the more input and discussion we have with the software community, whilst we're doing that, the better, because it means we can make sure that we meet the needs of the developer community. There's about 120 companies currently in the Khronos Group, everyone from Google and Apple all the way down to small startups. And Khronos is busy creating all of these native APIs. That's what we've been doing for over 10 years. OpenGL ES for 3D, OpenSL ES for audio, OpenMax for video. And Android and iOS, which between them make up over 90% of the mobile market, are increasingly adopting these native APIs and shipping those native APIs on their platforms. So WebGL was the first web standard that the Khronos Group created, and it was originally initiated by Vlad at Mozilla, and comes from the realization that finally we have a 3D API that's pretty well available everywhere. OpenGL and OpenGL is available everywhere. Meanwhile, JavaScript performance is getting quite good, and we have the canvas. So bringing those two together, binding OpenGL ES into JavaScript, using the canvas, and letting us to create a 3D context for the canvas is the essential idea behind WebGL. I'm sure many of you are familiar with this kind of stack, but this is how WebGL is implemented. The system vendors and the silicon vendors will typically provide the native API drivers to OpenGL, OpenGL ES, or perhaps Direct3D if it's a Windows platform. Then the browser vendor implements a WebGL engine inside the browser itself, so we don't need a plugin for the 3D capability. It sits alongside and is a peer to the HTML5 stack, CSS, and JavaScript. And that is accessible through JavaScript, either directly by JavaScript applications, or typically through some kind of middleware, JavaScript middleware, so a web developer doesn't have to learn every nook and cranny of the WebGL API, which is quite a hardware-centric API. It's not a typical web API, but a lot of those details can be hidden from web development community by using the appropriate middleware. And one of the most popular, and again, I've seen some presentations around at the show here, is 3.js. It's a JavaScript library that really makes use of the underlying WebGL quite straightforward and lets you get going quite quickly. So WebGL, the spec has been out a couple years. How are we doing in terms of availability in browsers? Well, the good news is that WebGL is now quite pervasively available. I think another 12 months, and we will genuinely have WebGL on every browser that you'll care about. But we're already making pretty good progress. In the spring, Microsoft made a significant announcement that they have adopted WebGL. Their statement is that everywhere that IE 11 is, the latest version of IE, WebGL will be there, fully accelerated and turned on by default. Google is now shipping WebGL in the Chrome browser on mobile as well as the desktop. Apple, ironically, because they're the spec editor, looked to be last to actually get it deployed by default. It's there in iOS and macOS, but in iOS, it's only exposed to the iAds platform. It is possible to toggle it on. And once you toggle it on, it's actually pretty good. Apple have a very good implementation, and hopefully they'll toggle it on by default pretty soon. So this is a demonstration just to prove that Microsoft are adopting WebGL. This is a Microsoft-crafted demonstration. It's kind of like a photo synth. So it's taking multiple photos, doing feature matching, so you can create a 3D environment, a point cloud, and render that through WebGL. This was something they showed at Build 2013, and it's a pretty cool app running fully accelerated in their IE11 beta. But I think the other big thing that's happening for WebGL is that we will truly get great WebGL performance on mobile over the next 12 months, as well as having great performance on desktop. This is another video I grabbed from the lab on my way here. This is a demo using WebGL. It's running in the Android browser right now on a Logan-based Android tablet. So this is the same GPU that we were showing before running the face, but here it's running WebGL in an optimized browser. This is the Unigine demo. So this is obviously a demo of a typical game type scene, but there's real-time lighting effects, there's real-time physics effects going on here, and you can see the complexity and the realism of the scene. You're finding it pretty hard to tell the difference between a native app and a browser. This is another simpler game, but I like the visuals of it. And again, it's pretty hard to tell the difference now between WebGL. This is running on an Android tablet, again, with Logan. You run this on Android, you run it on the desktop. The effects are the same. The performance is getting to be the same. So WebGL is not just a desktop thing. It's going to be a mobile thing everywhere, I think, in the next 12 months. So this means that for the first time, we actually have a genuine platform where we can write a 3D application once and have it run pretty well everywhere, on desktop, on mobile, on all of the OSs that primarily matter. Because if you look at the alternatives, the primary development APIs provided by the key platform vendors are different. And you might say, well, the platform vendors aren't particularly motivated to have their native apps wander off their platform onto the competitor's platform. So there's a variety of different programming languages, and I don't think there's any chance of those converging. If you use C or C++, which is available on most of those platforms, there is a diversity of native APIs. The Windows platform has DirectX rather than OpenGL. It's the web platform where we have everything we need for portable applications on all of these platforms now. So this is the first time in the known universe we've actually been able to write a 3D application and have it run with no modifications on this diversity of platforms. So I'm not going to go through the details here, but we'll upload these slides if you're interested. But this is the family tree, if you like, for OpenGL. The key thing is that WebGL 1.0, which is the version of WebGL that's shipping today, is derived from OpenGL ES2, which is in turn derived from OpenGL 2, which is a desktop API that was created about 10 years ago. So it's pretty good functionality, but there's room for more functionality to come in WebGL because the native APIs have been evolving steadily since 2004. So we're actively working on WebGL 2, which, no great surprise, is going to be based on OpenGL ES3. It's an active development now. Khronos does the development of WebGL in the open, and we welcome developer feedback. So the links are here. If you're interested to look at the drafts, give us feedback, how we're doing, that you'll be very welcome to do so. So WebGL 2 is going to use OpenGL ES3. Well, what is in OpenGL ES3? OpenGL ES3 was released about a year ago, the specifications, and the silicon, the mobile silicon that ships now with OpenGL ES3 is making its way into the market this year. It incorporates lots of features, actually, from the desktop OpenGL, OpenGL 3 and 4. We have 32-bit integers, 32-bit floats, non-power 2 textures, 3D textures, depth textures, so all of the, well, not all, but very much most of the texture capability on desktop machines will now be available in WebGL. Multiple render targets, occlusion queries. We think we're covering most of the requests that we've had for 3D functionality with WebGL 2 through OpenGL ES3. Also, OpenGL ES3 is more tightly defined than OpenGL ES2. We're trying to make compatibility as you go between multiple platforms tighter, and it is backwards compatible. But the number one developer request, and again, it's particularly relevant to the web community, is for a standardized texture compression format, because it really sucks if you have to download assets and you need multiple textures, which is often the biggest part of the asset package. If you need multiple versions of textures just because different chipsets support different formats. That's kind of gratuitous bandwidth wasting. So we have what we think will become a universal texture standard called ASTC, and it's awesome. It's great quality, and it has two independent dials. You can dial up the quality up and down depending on your bandwidth quality needs, and you can also dial the number of components within the texture. So you can have 1, 2, 3, or 4 component textures. A 4-component texture, typically RGB plus transparency alpha map. And because you can control each of those dials separately, it's going to meet, we think, the needs of pretty well every application out there. ASTC is beginning to ship. It's an OpenGL ES extension right now. We'll probably do the next version of OpenGL ES. Might be called OpenGL ES 3 point something. And hopefully, if we get good developer feedback on ASTC, the time might be right to build it into the core spec, and then it'll flow through into WebGL. So at this point, it might be worth just saying, well, W3C does most of the web standards. Why is Khronos doing these things like WebGL? We think it's a good and synergistic partnership between Khronos and W3C. Khronos is not trying to do general web standards, but where we think we can add value is where we're trying to bring detailed hardware capabilities up into the web environment. The Khronos community is where the hardware guys go. We're designing APIs that are the basis for designing chips that cost hundreds of $millions to build. So they're very tightly defined, full conformance tests with a deep insight into the architecture and the drivers that we need to effectively run this kind of silicon. But we're very committed to being a good citizen in the web community. We're opening up the web standards to be an open, publicly available process. And we're talking to the W3C folks to see where are the opportunities where we can bring these native standards and bind them up into JavaScript and help the web community access this well-defined hardware functionality. So what are some of the other standards that could be coming to a web browser near you relatively soon? One of the most interesting standards that we've been working on for a while at Khronos is called OpenCL. This is the compute API. This is a way for you to use parallel processing across any heterogeneous computing resources that you have in a platform. It can be CPUs, multi-core CPUs, GPUs, even DSPs, and other kinds of hardware on mobile SoCs. The way we do that is that we enable the developer to write a kernel of work, or many kernels of work, in a language that is basically C99. And then we have a couple of APIs, an API to discover what hardware is on your platform, and then a runtime API to take those kernels, compile them, and distribute them across any combination of computing resources that you have available to you. This means for the first time you can actually write a single source tree, and at runtime decide whether to run kernels on CPUs, GPUs, even hardware blocks, and DSPs. Now, OpenCL is another low-level API. Khronos, we try to keep as low-level to the silicon as possible, not to prejudge the way the market will go, whilst still providing portability and opportunity for differentiation. But OpenCL is a low-level API, so it's been used by quite a few higher-level languages. Python, C++ AMP has a compiler option to OpenCL. But there are a couple that are relevant to the web community. Intel has a project called Rivertrail, which is JavaScript language extensions, and that compiles down into OpenCL for execution. And then the Khronos standard WebCL, which is a JavaScript binding to the two APIs in the OpenCL framework. So WebCL enables the JavaScript programmer to write C kernels and then dispatch them onto available compute resources through a JavaScript API. So this is a simple demonstration. This is a WebGL app, two shiny objects in a scene. Now we've turned on deformation. There's a lot of floating point calculations to calculate the jelly-like deformations in this demo. Here, the floating point calculations are happening in JavaScript. And JavaScript is fast, but you put enough floating point into JavaScript, it will slow down eventually. Now, if you take off the floating point load from JavaScript onto the GPU using WebCL, the frame rate goes back up by a factor of 100. So we're now using the GPU for both compute and rendering. And obviously, this is a simple example, but you can imagine perhaps a game where you're using WebCL to accelerate your physics computation, and WebGL for the rendering. Again, we're really removing the barriers for a web page to be just as performant as a native application. So we have WebGL, is already shipping WebCL. We're planning to release the WebCL spec hopefully early next year. We're working on OpenGL extensions for vector acceleration. I will get to that in a second. But then we have these other native APIs, which are really on the input side, the camera and sensor and sensor fusion and vision processing. These are not initiated projects yet. We haven't completed the native APIs, so it's premature to bring them up into JavaScript. But we do see that once we have the native APIs deployed, each one of these APIs is quite suitable for bringing up into JavaScript. So I'm going to whiz through these because these aren't web APIs, but just to kind of give a flavor of the kind of things that we're working on to enable applications like augmented reality or vision-based applications. Stream Input is a sensor fusion API. It's a native API that lets a sensor vendor do high-quality sensor fusion under the covers, making use of all of the sensors in a platform to provide a high-quality, low-power fused sensor stream back to the application, along with contexts. So you know at the application level very simply whether the phone is being carried or being driven in a car or is in an elevator or is face down, face up on the table, things like that. We have OpenVX, which is a vision acceleration API. It's complementary to OpenCV, which is like the open source standard for vision processing. The key difference between OpenCV and OpenVX is designed to enable efficient hardware acceleration. You can describe the graph of vision operations you want to occur in a series of nodes in a DAG. That gives the opportunity for the implementer to fuse nodes, to compile nodes, or even run nodes on dedicated hardware. So this is going to be necessary to enabling always-on vision processing in mobile devices. And the last of the three is a camera API. There are some camera APIs out there, but most of them are designed for simple point and shoot. If we're doing things like augmented reality or HDR photography, we need much more control over the lens, the sensor, the aperture, and how the images, a stream of images, is captured from that sensor array. We have APIs like OpenCL for pre-processing. We have APIs like OpenVX for post-processing, but we've never had a standard API for that level of control over the camera operation itself. And Khronos has just initiated a camera API for that purpose. It's so new, we don't even have a name or a logo yet, but that's intended for launch probably by the end of next year. So if we're creating an application like augmented reality, using native APIs, for the first time, we can use the native APIs that are open standards to create a augmented reality flow, 100% acceleration with 100% open portable APIs. So we'd like to start working and bringing that capability up into the browser. Now, there's actually a community group that are just discussing these kinds of topics. It's a W3C community group. It's the AR, Augmented Web community group. I've put the link in there. So if this is of interest to you, the Khronos guys and the community group guys are talking very closely, so that would be a great place to put your input. So, next topic is a transmission format. I mentioned earlier that there's no point having all the performance in the client if we can't get the 3D assets to be rendered down into the client in an efficient and effective way. And 3D is kind of the odd man out. All of the other media types, they already have a streaming and compression format. And it's interesting, if you look back, when those streaming and compression formats became widespread, significant things happened in the market around those media types. So MP3 spawned Napster, H.264 for video spawned YouTube, JPEG images, Facebook, Instagram, etc. We don't have our compressed streaming format to enable our social media moment for 3D. So we're trying to create that at Khronos. It's called glTF, OpenGL transmission format. It's a runtime neutral compression format. It's just a bucket of assets. It includes geometry, texture, animations, but it doesn't imply any runtime. It's intended to be a very lightweight format that's almost directly, I call it shovel-ready for WebGL. You can almost take the format directly off the net and load it into a WebGL app, any WebGL app, with very little processing. Because on mobile devices, if you have a format that might be very compact, but needs a lot of unpacking and processing on client, that can be as slow as waiting for a slow network and can take power. So we're trying to keep things very efficient. And we're trying to build an ecosystem here. So we have Collada. Some of you might be familiar with that. It's another Khronos standard. Collada is not a transmission format. It's an asset interchange format for authoring tools. It's human readable, it's big, it's archive ready. But the tools are using it. And we have now created an open source exporter for Collada. So any of the tools that you're using, you have access to high quality Collada export. We have a Collada to glTF translator. So if you have your assets in Collada, you can use our open source project and convert them directly to glTF. But of course, other authoring formats can be converted to glTF too. glTF runs directly into WebGL. We even now have a 3.js importer, and we're working with the REST3D initiative. And of course, you can take glTF to native apps as well. WebGL is becoming pervasive. We're actually beginning to see more and more tools, authoring tools being built in WebGL, so we complete an upward virtuous spiral. Now, all of this is happening in open source. I've put the links here. So if any of this is interest to you, please help us and get involved. We're also using, glTF doesn't include compression. Version 1.0, it's just an efficient way to pack assets and to have it easily loadable into WebGL. But we want to go one step further. We want to have compression and streaming. There's quite a range of compression technologies out there in the industry. The baseline is gzip. You can gzip 3D assets just like any other assets, but there's a lot of a priori knowledge in 3D assets that you can use to be a lot more efficient than gzip. One of the longest standing initiatives is from the MPEG group, who it's interesting, they were the ones that created all those other media type compression formats. So it's SC3DMC, and they have committed to make that available to the industry royalty free. There's an open source converter now into glTF, and we're using glTF as a test bed to discover what of all these various compression technologies in the industry are going to be most effective. And we might not end up with just one, and if so, which types of compression are best for different types of models and types of applications. We've just started this initiative, so these are very early results. These are not conclusions. These are like work in progress. But again, we're doing this in open source. We're doing this in the open. If this is of interest to you, be very welcome to get involved. But some interesting results, even though they're early. A gzip file here can compress down to 26%. Open3D GC, which is the MPEG technology, can take it down to 5% or 3% of the original asset size. So we're eliminating 97% of your download time, which is a pretty worthwhile result. But we are beginning to look at decoding speed too. As I mentioned, if things take too long to decode, the advantage, particularly on mobile devices, evaporates. OpenCTM is kind of interesting. It uses LZMA, but LZMA takes an eternity of time to decompress on a mobile device. So, one possible outcome of all of this is that the silicon vendors might start building LZMA decoders into hardware like we build H.264 decoders into hardware today, if we can get this pervasive enough. So it's a good, interesting project that's underway. So my last topic is path rendering. This is a project that we've been working on at NVIDIA for several years now. We're making good progress. And this is bringing path rendering acceleration into OpenGL and OpenGL-ES to enable native acceleration of established standards like SVG and Canvas. So the various ways that you can render vector graphics, the traditional way is to use the CPU. CPU scanline renderers can be very high quality, but of course, if you're rendering a lot of graphics, particularly to a high resolution screen, it can heavily load the CPU, not only slow rendering, also preventing the application from using the CPU too. There have been several attempts from NVIDIA and others in the past to turn the paths, the vector paths, the Bezier curves, etc., into polygons and send a bucket load of polygons down to the GPU. This actually turned out, to everyone's surprise, not to be that effective because you're still loading the CPU to do the tessellation. The tessellation costs you some quality, and there's still a lot of data to shovel between the CPU and the GPU. So we've ended up in a place where we've created a path definition. We can take a Bezier curve, create a path definition that we can pass directly, very compactly, to the GPU, and the GPU will be able to render that path entirely on the GPU with no further interaction required on the CPU. So we're at total offload and very minimum bandwidth between CPU and GPU. So how does that work? Well, the clever source is that we figured out how to run shaders on the GPU to evaluate a Bezier curve, to figure out where the curve is, whether we're inside and outside a region. And we can turn that serial evaluation of that curve into a massively parallel evaluation using the parallel architecture of the GPU that we have available. So the way we do it is we create a path and we load that into the stencil buffer. And then we can push any kind of rendering that we want through that stencil in the stencil buffer that is representative of the path. So we call it stencil then cover. We can use the GPU anti-aliasing, so we get 8 or 16 or higher, harder anti-aliasing, so we get very high quality. So there are a number of advantages. The quality is significantly higher using the GPU. The GPU is built to do this kind of thing, so it's not surprising. For example, we offered jitter-sampled anti-aliasing for free. We're not having to make any approximations to the curve evaluation because we're just doing brute force in parallel, accurate evaluations of the curves. We can have multiple samples per color sample and per stencil sample, so we don't get conflation effects. And everything is being calculated at maximum accuracy. So even do torture use case gradient filters, everything is accurate and precisely correct. So this is and of course it goes faster. That's kind of the obvious advantage. We're finding it depends on the scene, but it's typically between 10 and 100 times faster than a software renderer. So this is a GPU accelerator. It's running at 800 frames per second. These are the control points on the curves. And the video here, we bring up some 2D renderers. This is the direct 2D using the GPU, but they use tessellation. And it's running at, if you can see it, it's running at 66 frames per second, so it's 10 times slower. Now we're selecting Skia, which is one of the best software renderers. That was running about 10 times slower as well. Cairo runs at 43 frames per second, so that's getting to be 20 times slower. The Qt, the Qt renderer, again, much slower. So better quality and faster performance. We can also bring new functionality, and we'd love to work with the SVG folks to see if we can fold this into future versions of SVG, perhaps. Because we have the path in the stencil buffer, we can use the stencil buffer and OR it with other things. So we can take a complex path and use a complex path as a clipping path. We can actually do projective transformations because we have the full power of the matrix hardware in the GPU. We're not limited to planar 2D. We can actually do sRGB correct rendering. We can actually run shaders through the stencil, so we can actually begin to do 3D effects like bump mapping with light sources. And the depth buffer is fully sustained, so we can actually begin to mix 2D and 3D. And this is a garish but simple but example of we have a genuine 3D object and 2D objects being assigned with a perspective, and everything is being rendered correctly. So we think this is a significant set of advantages for vector rendering. We actually have an open source SVG renderer. It's not complete yet, but the link is there. If you're interested to help us develop that, you'll be extremely welcome. There's a bunch of information up on the NVIDIA website. So this path rendering is built into our production OpenGL drivers. So if you have the latest OpenGL drivers on your NVIDIA card, you have access to the NVPR extension, so you can try it out if you want. But of course, a proprietary extension is not that interesting. So NVIDIA is committed to making this an open standard. We have the vendor extension that is now being proven, where we have already taken it to the Khronos Group for their consideration as a standardized extension to OpenGL and OpenGL ES. We hope that will happen. And then, even though then we have these high-density screens, and the mobile silicon node is coming up to be capable of running this extension, so we can get really pervasive vector acceleration across desktop and mobile devices. The time is right for this to happen. And lastly, this is coming to mobile, so this is another video from the lab. So this is the vector extension running a web page. So we've captured the web page and put it into SVG for the purposes, so we're not waiting on the network. This is running on Logan. So again, this is running on an Android tablet, a mobile device. We have a complete web page. We can zoom right in. This is a genuine path rendering. This is not bitmaps. And of course, you wouldn't render the complete web page. You'd render the visible parts. We can turn on the warping just to show that things are being warped here and rendered in the GPU. And we can zoom in again. Everything is being rendered at full resolution through the path rendering extension. And this is running on an Android device. So again, this isn't a desktop technology anymore. This is mobile technology. So that's it. Hopefully that was useful. So just a recap. So open standards such as WebGL and WebCL, enabling JavaScript developers to reach into the GPU for graphics and compute. We're going to need GPU acceleration soon for advanced web applications that want to do augmented reality vision applications, reaching into the sensors and cameras and vision acceleration that's coming in mobile devices. And we very much want to work with the web community to make that happen. The path rendering extension will enable the SVG and canvas renderers to take full use of the GPU. We're working on compression and streaming standards for 3D, so we can get these assets across the network efficiently. I think the web community and the hardware community have a real opportunity to work together and not reinvent the wheel and just move the industry forward. And the Khronos Group is committed to work with the web community to make that happen. Okay, thank you very much. So we have a couple minutes if there are any questions. Yep.
Is there a working prototype browser for the OpenCL stuff, WebCL stuff?
Yes, there are several, in fact. Samsung and Nokia. In fact, we'll post these slides on Khronos and here at the show. The link is in there on that slide. So if you search for WebCL Samsung, that's the most up-to-date one. You'll find their open source implementation. It's based on WebKit. Yep.
The last demo that you showed, the camera device, in the
Yeah.
What type of devices currently support
So these devices, this extension assumes that you can run CUDA or OpenCL. So basically, it means you need a unified shader. But the good news is that pretty well every mobile device now, shipping this year, is now capable of this. So I would say during 2014, it will be pervasive. The GPU capability will be pervasive to be able to run this extension. I would say we're probably like 60 to 70% pervasiveness now. By the end of next year, we'll be 100%. For this project, this is an NVIDIA one. So if you just go to the links here, but you just search for NVIDIA path rendering, you'll find it. Yep.
When you offload SVG to the GPU, would the browser still be able to get back information about, say, the bounding box or interactivity, etc.? Would that be affected, or would that still all be?
Yes, that's a great question, Doug. So we have all the queries that we think we need. In fact, at SVG Open last year, we found one that we were missing. So we've built that in. So all the bounding boxes, everything that you would need for integrating SVG into a larger application should be there. But take a look and let us know if you've missed anything. But we've tried to cover that, yes. Anything else? Okay, thanks everyone. Oh, I'm sorry. We can do hit detection. Yes, in fact, we have a white paper on that. That's on the NVIDIA website, so you might want to take a look at that. Okay, thanks everyone.